guys, I just wanted to talk to you a little bit more about the really cool thing that Doc talked about, or hinted at, in his last, in the Atwood's machine video. So this was the setup. We had this base that had a mass of 4m, the pulley had a mass of 3m, and then we had like this guy, m on the left and 2m on the right, and then even though he picked x to be up, right, you can look at that and I'm sure that you see that it's going to accelerate down on the right and up on the left. And so I'm just going to do that here. And remember, he got something like the magnitude of that acceleration was 2/9 g. So the thing that he ended with is he said, look, this whole entire thing has a weight of 10 mg, right? And he measured this normal force on the whole thing as 88/9 mg. He said, okay, so it's not just balancing out, right? And so this was the discussion that I wanted to have. Like, why is the normal force not equal to the weight? And it is because inside there is some internal accelerations happening. So to explore this, like, I want to talk about sort of why did you even think that the normal force should be equal to 10 mg, right? And that's because you're used to rigid bodies. In a rigid body situation, that normal force would be equal to it because we know that, you know, all the internal forces in those rigid bodies would cancel out, right? And so, right, all internal forces cancel in a rigid body, right? But this setup right here is absolutely not a rigid body. There is some internal acceleration going on. And so I actually want to do a little bit of a calculation to show you how this stuff sort of beautifully comes together. So to do that, I want you to actually think back on center of mass. And is the center of mass of this system accelerating? And I think if you think for a second, you will realize it is. Because that thing's going this way, that thing's going this way. Now this 3m, this 4m, right? These are not accelerating, right? But our mass on the left is accelerating up. Our mass on the right is accelerating down. So I want to actually calculate the acceleration of our center of mass, okay? And if you remember how that works, it's m1 a1 plus m2 a2 m3 a3 plus m4 a4 divided by, right, the sum of the masses, the total mass. Okay, so let's start on the left here, and you know, let's call that direction negative, that direction positive, okay? So my left hand guy has a mass m and an acceleration negative a. My right hand guy has a mass 2m and acceleration positive a. My 3m has no acceleration, and my 4m has no acceleration, and we know that the total mass is 10m. So what do I get? My center of mass's acceleration is 2ma minus ma divided by 10m. M's go schwa schwa. And do you remember what he calculated as A? A was 2/9 of g. And then if we divide by 10, we get this. So what this says is that the acceleration of the center of mass of the whole system is 2/90 g, okay? Okay, so now this is getting kind of cool. So I'm just gonna write that up here because I'm on a new slide. So it's 2/90 g. Let's see if we can relate this to anything else from the problem. So where have we ever seen acceleration due to center of mass? You know, when I think about center of masses moving, honestly, this is the equation that comes to mind. I hope that it comes to your mind too. So that's nice. That's just sort of talking about total momentum of a system is the total mass of a system times the center of mass's velocity, right? So if I'm thinking about the acceleration of center of mass, I just have to take a derivative, time derivative of both sides. My mass is staying constant. And so, right, that is the thing that I'm sort of trying to explore. So on this side, I'm going to get m total times the acceleration of the center of mass. Now, I hope that if you see dp dt, then you think the net force, okay? So this is kind of cute. So the net force is equal to the total mass times the acceleration of the center of mass. So that shouldn't come as a surprise, that equation, okay? Let's plug in what we calculated for the center of masses, acceleration, yeah. So we have the 10m, and our acceleration was 2/90 of g. So what is that? It is 2/9 mg. That's the net force. So I will remind you, in the beginning we found that it was 10 mg and then only 88/9 mg up. So what's the difference? It's 2/9 mg. Cute, huh?